Hello, I'll go ahead and start. I'm Jim Tommaney, I'm CTO at InfiniDB. We have an open source technology that offers high-speed analytic queries. It's an InfiniDB storage engine. I've been with InfiniDB for about 8 years, project architect role, just spending time talking about the technology and building out the technology. So there's a lot to talk about. It is a MySQL storage engine, but it's non-standard. And so we'll talk about the differences and what parts are the same and what parts are different. It's a distributed engine, allows for scaling workloads across all available cores on a single server, as well as all available cores on a cluster of servers. It's not truly a database from the standpoint, so it doesn't approach things from the same standpoint as what Maria does. So it's not better than Maria, it's just different. Allows for linear scaling. We are open source, GPL v2. We do have a subscription model as well, but it's an open core model. The core technology is available to use without restrictions on performance or syntax or scale. So we want to believe we're very open in terms of how people can use it. We run on Amazon, we run on-premise, we run as part of a Hadoop infrastructure as well, so we drop into Hadoop. We support basically the vast majority of the MySQL syntax. In addition, we've added some analytic functions, windowing functions that are part of what can be done in our engine that are part of the standard MySQL. There are some specific transaction-oriented functions and behaviors that are part of MySQL, MariaDB, that we don't support. So things like nested cursors within procedures, that's not supported in our engine, things like that. And to give a sense, this is the idea: you can take virtually any data source, load it in an InfiniDB system, and do predictive analytics, satisfy dimensional drill downs for traditional BI processing. Virtually any use of the data that can be supported by SQL. A little bit about kind of where we fit. And there's a couple terms on here we'll talk through, but we talk about user modules and we talk about performance modules. And for us, that's just internal process. We do have a two-tier architecture. It can all run on a single server, or it can run in a scale-out model as well. When you talk about sort of what goes on at the user module layer, there's really two software components running side by side that work together to act as a user module. It's the MySQL and the InfiniDB. We've got a process called EXE Manager. But this is sort of a general flow here on how things work. So the SQL query will come in, it'll be a user validation, initial parsing of the SQL, and initial optimization of the SQL take place there. And then we've got a handler class. So those familiar with MySQL, we have a non-standard handler class that's part of our implementation. And what happens here is that effectively at that point, the InfiniDB engine will take over execution of the query. And MySQL is involved again for returning the final results through the MySQL client, and the final sort is applied by the MySQL as well. So just to give a sense on it, and then we'll talk about the performance module. That's our distributed layer as well. But just to give a sense of where we fit in the MySQL stack. It's very familiar syntax in terms of create table engine equals InfiniDB. One of the things that's different, though, is we don't support indexes. We don't support partitioning. We do partitioning internally, but we don't support partition syntax. So those things don't show up in our engine. So when we talk about InfiniDB, sort of the design principles, we talk about scalable, fast, simple. Those are sort of the targets to shoot for. The MySQL capability is it's built around the idea. It's a very simple engine, very easy to use. And we didn't want to lose that. So that was been one of the core driving principles for building out the technology. And we'll talk about the architecture. We'll kind of talk about it in these pieces a little bit. So we'll talk about sort of the scalability of the parallelism. So this is another picture here of the user modules and performance modules. And effectively, you can have the user module, performance module, running on a single server, or you can have it in a distributed architecture. And typically, if it's a large enough distribution, we'll have the user modules on one server and performance modules on another server, although that's really an implementation decision. It doesn't have to be that way. At a very high level, the user module really is an SQL engine, understands SQL itself. The performance module really doesn't ever see the entire SQL text by itself. Instead, it's working on a subset of the query, working on some data operations that are block-oriented. And sort of the way to think about it, I think there's some better slides, but it's basically if you need to do a specific command to get a specific number of rows, basically a thread will be designated to work on that. I'm not going to walk through all the detail here, but this will be well for the slides. But the use module is the SQL layer. Performance module really deals in the data blocks. It's all C++. We can basically leverage all available cores on a single server, all available cores in the scale-out model. Internally, we talk about the term primitives, and the process running at the most distributed layer is actually called primproc for primitive processor. So in support of a query, basically, the UM will take the query, receive it, parse it, do our own optimizations for our engine, and we'll basically distribute that workload across all available cores. Typically, a query can be broken down into thousands, tens of thousands, or hundreds of thousands of very small primitives, depending on exactly how many rows are required, how much is required for the query. So it's intended for accelerating large queries. I think you're probably already starting to get that, rather than accelerating, small queries, individual reads and writes. And this is kind of a little graphic. So there's the idea there's a thread pool. When you talk about the performance module layer, there's basically a thread queue. So there's a fixed number of threads running on the performance module. And that doesn't change regardless of the query workload. So instead, what happens is the thread will go, so the job will be issued, it'll go down into this thread. Basically, the next available thread in that thread pool will pick up that job, operate on it, and return net results back out to the user module for final consumption. And so for queries that look like group by, queries that look like sums or counts, the typical bytes back out are much smaller. So it's very well suited for drill down some, basically dealing with very large data sets and typical, output results are designed to be summaries or something readable by a human, or some abstract of the underlying data. You found the pattern rather than extracting all of the data. So one of the side effects or characteristics of that is actually at the PM layer, it can run at 100% CPU utilization for hours on end, and that's actually a normal use of the system, and it doesn't really indicate that anything's gone wrong. So that's slightly different from I have a lot of background in Oracle, and if you hit that metric, the system had gone south and it would need rebooting. And just a little more distinction on here. So there's other kind of distributed technologies that are sort of a database layer on top of another database layer, where effectively the worker process, if you will, is effectively running an SQL statement, and it might be based on a subset of the data. But for ours, it's just a completely different model. So we're distinct from how Greenplumber and Teza work at the most distributed layer. And the distinction that basically comes through in terms of sort of thread allocations for an Oracle or other systems that have parallelization. You'll allocate threads in support of a query. For us, there's no dynamic allocation of threads at the PM layer. Instead, they're working through that queuing model.
That basement also have MVVs working, that's it. Okay,
yeah. Yeah, we're not the only one that's out there doing this, but it is different than sort of how few of these guys have done it. So fast is really a function of two things. So certainly the parallelism and the scalability, but the other part is basically column storage on disk. So how we store the data on disk is part of our performance story. So this slide I used to have to explain at length because nobody had ever heard of a column database, but I'm sure most people are at least somewhat familiar with the idea. But it's basically that for a given record, we store each column in a discrete file separately. So we can do I/O for the state field for record 1 without doing any I/O for any of the other columns. Internally, we store everything by offset. So basically, within a structure, the first position for the state field maps directly to the first position for the zip field. Excuse me. And that's part of our experience. So we'll walk through some more examples of what goes on here. But It allows for a couple things. So certainly the I/O elimination, we can focus just on the columns that we're using. And then we also get a good compression because we can compress sort of similar values, and we don't have to typically deal with this kind of we typically get a very good compression ratio. So maybe 6x to 10x is a reasonable compression ratio because we'll compress basically the state field by itself or the zip field.
And explain the compression, but assume that you want to access row number 2.
Right.
And the zip field. But you need to do a lot of decompression of lots of things in the same block just to be able to find the offset for the 95.
So absolutely. So if you need to only get row 2, then we're the worst engine possible for that because the trade-off exactly what you're noticing. So we would have to read key 1, decompress key 1, read key 2. We would actually read a range of rows here and decompress, read a range of rows and decompress. So for a row-by-row access model, we're less efficient than MariaDB. And so when we talk about it's not better, it's different, right? So that's the whole goal.
There looks like there are certain new databases. They are storing both rows and columns.
There are.
At the same time.
Yes.
And because the cost of storage is not that cheap.
It's becoming cheaper, certainly. Although the size of data is still a problem in many cases.
Yeah, but you may rely on a network storage.
Yeah, no,
if everything is storing local disk, that's probably a problem.
So I think that's definitely an interesting idea, right? So that it adds more capability to the system.
Yeah, it's like you do some pre-computation, and when you try to retrieve your data on disk, it's much faster.
Yeah.
But of course, updates will go.
There's no free lunch. Yeah. There's overhead.
That's absolutely true. Okay, so it's basically a two-dimensional partitioning model as well. So we'll partition by column, and there's another term out there. So people talk about column family, HBase or Cassandra. So the storage on disk doesn't look anything like that. Instead, it's much closer to Parexel, Vertica, or the Parquet file formats. And we also partition horizontally by range of rows. So as data comes in, we'll actually create 8 million row chunks of the data, and we'll store each one separately. And there's kind of a rule of thumb here. So if you've got about 10 terabyte, fact table, we'll break that down between about 150K and 300K discrete objects on disk. And we've got metadata that we store about each of those. So we've got min-max values and things like that allow for partition elimination in many cases.
You store each table in different files.
Yes. Yeah. And so just kind of a little walkthrough just on, this is sort of the concept of what's going on in the primitive. The primitive is doing specific operations in support of a query. So we talk about columns. You can reference columns independently. Internally, a horizontal partition is, internally we call an extent, but it's a similar concept. Basically, it's a collection of 8 million rows. But you could have a query that effectively, we don't do a full table scan. That doesn't exist unless you've said select star with no predicate, of course. But instead, we'll actually, for a query with 3 filters and maybe 7 more columns being projected, we'll apply filter 1, and that may or may not restrict the rows. And we can sometimes do I/O elimination or partition elimination to identify a specific range. Filter 2 might further limit the rows. We'll do I/O in support of filter 3 after we've determined what's required from filter 2. So there's sort of the idea of a just-in-time materialization that takes place. And then assuming filter 3 narrows it down to that narrowest range, we'll just do projection out of that collection of data. So that's part of the secret sauce around the I/O. And simple, so we can talk about, we want to have the simplicity of the MySQL storage engine. We want to have it easy to use rather than more difficult. So, part of the design decision is just to make as much as we could automated and behind the scenes for you. So, the column storage is just create table engine equals and InfiniDB, and underneath the coverage we store it, so it's transparent to the developer what's going on there. The compression is on by default. We use Snappy. We've got, we're going to put some other things in at the end of the year, but that's what's in place right now. But that's on by default, and typically we haven't had anyone need to change that for most workloads. No indexes are required. So it's that extent map that happens automatically, that extent map behavior. We also will distribute the work across all available disk and server resources. So when you set it up, you can actually configure it with an arbitrary number of data mount points, and we'll actually distribute the data across all of those for you. There's actually some flexibility on loads you can do. So we aren't great on row-by-row insertions. That's not a strong point for us. Billion-row fact table, you basically need to load via CP import to support, to get there. CP import is our batch-oriented load method. But that runs in, you can run a number of different nodes. You can run it from any of the servers in the cluster, and it will automatically distribute the workload across there. Or you can run it local to the PM, and it will load the data local to that PM. So you can run it basically a fully distributed job or a local job. And you can run, on nodes 1, 3, and 5, you can have a job run at 1 o'clock, and then, 3 minutes later, you can have a job run on the other node. So they can run independently as well on each node. And when you get to, the ultimate scalability, you want to have not have a single load point in support of that. And in terms of distribution of work, basically virtually all queries break down into very granular jobs, and that allows for a very good distribution of work. And so it's typically, you don't have to pay attention to the idea of, well, this query is parallel 4 ways and this query is parallel 8 ways. Instead, every query is basically, broken down to a very large number of very small primitives. And so internally we handle that queue. And you can prioritize jobs. You can actually have class of queries or class of users that have a higher priority in that queue. And you can have other queries that are level priority.
How do you handle all the different MariaDB functions, MySQL functions? That we have lots of those. If you basically have your own SQL engine underneath, you have some problems, or do you actually call the value, the item?
So we actually rewrote the SQL functions themselves. So things like the date format or whichever of those have all been rewritten as a C++ distributed library. So we wanted to have those be, we wanted those to fit in what was handled within the primitive processing, and so it's designed to be sort of a small piece of code, and we want to avoid kind of row by row processing costs, and so that we were sort of forced to do that. You can actually set up the system if, for example, there was a MariaDB function that was added that we don't support, that we haven't distributed. You can actually set it up to allow that to run, so you can work through a couple different models, but the fastest way is if we've got it coded in our distributed layer. So kind of what's new. So previously we were not great open source citizens. October 15th last year we went open source with version 4 of our product. We had a community version that was actually a couple versions behind. We fixed that. And now we're pretty close to being a very friendly open source company. We used to be called Cowpont, and the product was InfiniDB. We all like the product name better than the company name, so we dropped the company name. We had a new round of funding happen this year, blah, blah, blah. So we did offer something that's new for us, is InfiniDB for Hadoop, and that's actually InfiniDB running natively on a Hadoop stack, so reading and writing to the HDFS file system. It follows the same processing model, right? So it works the same for us, but we just read and write to the HDFS rather than local file system. And we added analytic functions as part of version 4 as well in the October timeframe. I got a little bit of preview on a couple of those things. So we did a benchmark. We had a third-party do that came out today, and I think I've got one slide to talk about that. But it runs faster than the other competitive offerings in SQL for Hadoop, so faster than Impala or Hive or Presto. So Impala actually does well for queries that match its partition key. So if you partition and you run a query against that partition key, it actually runs well, and in some cases actually faster than InfiniDB. But in other cases, we're far faster than Impala. So Impala is good technology. We're probably better for an ad hoc usage than where Impala fits. And the net result is you've got InfiniDB, you've got Hadoop as a MySQL data source. So anywhere you can read and write, you want to expose Hadoop data, you can through MySQL. And it is a non-MapReduce process when you drop it in. So you'll basically connect to the user module process and run that. So we avoid using the MapReduce as part of the engine. And if you talk about name nodes and data nodes in the Hadoop world, you would map a user module process to a name node and a performance module process to as many data nodes as you wanted to.
So do you support streaming?
Streaming data?
Yes. Actually, on the other side of streaming, we're streaming in and streaming out to HDFS.
So not natively within our capabilities, right? So we do have tools to use Scoop to move data back and forth. So you can expose data in our engine and make it available through Scoop to HDFS processes, and you can use Scoop to load data in parallel into our engine, but it's not truly a streaming capability. And you can run with us, you can run DML against the HDFS file system, but it's not fast because you have to alter effectively. There is no, it's a write once file system, so we actually have to you change one record, we have to rewrite a large block. And so it's not fast, it's capable, but not fast.
Okay, thank you.
Okay. So the idea of the value proposition, so it's just, you can get at data easily. We actually compete very well with Cloudera, and we're looking at partnerships in the Hadoop distribution space. And it's sort of the idea that, well, what's Hadoop good at? So it's very cost-effective storage. Certainly you can run a MapReduce job, and it's a robust job, and it'll run, regardless of hardware issues or anything like that. But in terms of SQL, analytics, it's not real time today. You can do things in batch, but it's just not real time, and we think we can help with that. This is a quick extract of the benchmark that came out, so this is the URL to get to it. But what we did is ran versus, so this is a pretty straightforward analytic query, just grouping by year and month and doing a count distinct of visits. So it's a very traditional kind of metric for an ad serving or traffic, counting traffic on a website. But the numbers are a little hard to read here, but InfiniDB was 6.9 seconds. This was Impala, that was 69 seconds. And Presto was 147 seconds. And this is actually syntax that's supported, excuse me, by Hive, but we didn't test it here because it was running in literally was longer than an hour to run, so we didn't run it. Let's see. This is a little sense of the new feature set, the analytic functions, and this is about we won't spend more than a minute or two on this, but this is an idea of the capabilities of the system. But there's a couple terms of frame and partition. So you've got an example query here that talks about this, and it looks a little, if you're not familiar with the syntax, it looks a little weird. There's a select XY, sum XY, and then some unknown syntax if you're not familiar with it. But there's a term partition that shows up here, and then a range declaration that talks about a range of rows. And there's just a quick graphic that will walk through what those mean. But basically, it's selected XY and a sum of XY over this partition. So the partition is partitioned by Y. So that's the values 1, values 2, and values 3. So we've got 3 partitions. So it maps directly to a group by in terms of what you can include in a partition, but it actually doesn't collapse the rows. So that's the one distinction. And so those are the partitions based on this syntax. And then there's a declaration here, range between current row and unbounded following. So it's this row and anyone after, right? And so you've got row 1 has got a frame is actually all the following rows. For row 2, the frame is actually that row plus 2 others, and smaller ranges for each of the following. And you can declare that as a moving average. You can declare, in either direction. This is also used for top-end style queries and those sorts of things. But just a little sense of what's possible with the syntax.
So when InfiniDB working with Hadoop,
yeah.
How does it know or get to know the schema?
So,
Yeah, because Hadoop HDF is a schema.
right.
And when InfiniDB working with it, how does it get to know schema?
So it's not automatic. It's still create table engine equals InfiniDB. So it's still a traditional declarative syntax.
Oh, I see. Also, that's also the way how in parallel works. Right?
Yeah. So it's long term we think we're going to get better, but right now it's
very painful.
It's medium painful.
So we introduced dynamic columns just to be able to only have one grade and it works for any table.
Yeah. So we're not everywhere we want to be, but that's where we are today. How about that?
Yeah, working with Hadoop is a huge opportunity.
Yeah, we think it's interesting. So it's for us it's kind of weird. So our processing model was effectively unchanged. We really didn't change anything other than validate that the installation would go through the steps to make sure it installed properly and ran properly. We had to make a couple changes around supporting VML because it's just a fundamentally different operation. But the reads and writes and support of the queries is really the same between running on local disk and on-premise or on Amazon or on HDFS. Let's see. Oh, sorry, a few more clicks to go through. So a little bit about who's using it and when to use it. So subset of the customers, we've got I think north of 50 customers so far. Some clusters in a few areas. So certainly people doing web analytics, tracking online traffic, that's definitely a strong suit. Some customers who sell into the telco space, we've got some nice presence there. Let's see, online games, one of our largest customers is GameLoft. They've got north of 100 terabytes, 25 node cluster. There's a genomics on here. Genus does animal genomics. It's not in here, but in some in the airline industry is a recent one. So there's some, we've got a nice mix of customers. And it's been about 4 years, we've been out in the market for about 4 years. And, so we are, we talked about different, we're different, we're not better, we're different. So in terms of where we should be used and where we shouldn't be used, so certainly, we're not well suited for transactional workloads. So the idea of putting and getting individual records, there's a ton more overhead for us than other systems. But if you talk about the idea, well, what's a general purpose database? Well, it's the old Oracles of the world doing transactional workloads and also doing reporting workloads, and quite frankly, the general purpose databases really aren't best of breed anymore, right? They've been replaced for transactional workloads, and they've been replaced for analytic workloads, in my opinion. But we're definitely well suited off to the right. And kind of the standpoint here is, well, hey, what's the size of your query? Effectively, how many rows are being pulled into the analysis? So if you're off to the left here, 1 or 100, it's we're not a great engine for that. If you're off to the right, we're typically going to be far more efficient around I/O characteristics than other systems. And what we found is there's really sort of no average query. You can't say that number in the middle, that the average query is 150 million. That's the average query, because it's not an average, right? You can't average between the two. The challenge is definitely at the extremes. In almost all cases, people have workloads on the left-hand side, and in many cases on the right-hand side. So what it typically means from an implementation standpoint is that we're not going to be a standalone solution for everything we need. In almost all cases, there's a transactional system in front of us. In some cases, for customers, they've got data coming up with a log system, and that's effectively the transaction system, so they don't really have one. But in almost all cases, there's a data source that's external to InfiniDB. And just kind of rules of thumb, if you talk about columnar databases like ours, how would they fit for single record lookups? Well, we're at least 10x worse around I/O characteristics. And typically for large access patterns, we typically can generate about an order of magnitude less I/O in support of given query. So we talk about kind of benefits. So we talk about consistent query performance and delivering real-time access to very large data sets. When we talk about consistent, that's sort of the idea that you've got a query against the living month of your data set. It's got 100 million rows in it. If you're drilling down by sort of these filters or that filter, it's going to take, you know, maybe, let's say the number is 5 seconds to run the query. If you change the filters, what you'll typically find is it takes about the same time. It doesn't really jump to, you know, 50 seconds under different circumstances. You get a very consistent response time. Now, certainly you can plug in a query that'll run in 10 seconds. You can plug in a query where you add some more filters, maybe narrows the rows down, and that might run in 3 seconds, but it's not really going to typically jump to, you know, you don't have the same kind of dichotomy between an index access and a full table scan. You're sort of out of that business. Certainly the linear scale. We've got, you know, a lot of customers, you know, use us to allow drilling down all the way to the raw data, right? So instead of having to present data back in aggregates and only the aggregates, they can store the data in our system and basically do on-the-fly roll-ups or on-the-fly aggregates. So Vodafone's kind of an example of that. They're doing aggregates with MySQL to support their BI systems. They have a large collection of you know, dimensions they reported, and it took them literally 8 days to build all the aggregates. And what they did is actually stop building aggregates, put the data in our system, and basically ran us and delivered, you know, fed their BI system directly from our engine. So they were getting, you know, typically single-digit number of second response time on queries, but they avoided that very long build-out time on their aggregates. I think this is my last slide, but this is sort of just a summary of the notes, but certainly scalable, consistent, simple to use, open source. Any questions? Good so far?
The master-slave on the architecture.
So there's it's based, there's a master and then there's a failover. So it's internally, there's you know, writes are synchronized, so we don't really intend to support thousands of writes per second. That's not something we're capable of. Because of our batch-oriented load system, we can actually load, you know, we can load in some cases millions of rows per second, but not millions of operations per second. So we do have a single point that synchronizes writes, and there's a backup for that, and you can have additional backups for that. So it's a master with failover.
You spoke about efficiency. Can you talk about what kinds of audio bandwidths you can achieve and what kind of processing utilizations?
So you know, there's the number of combinations are very large in terms of, you know, mix between CPU and bandwidth. For kind of a data point, you know, we could easily have an so we can have an 8-core system basically fully consume dual fiber channel connections down to disk, if that's one data point. The other way to kind of think about it is it's sort of what's the cost for a disk operation versus a cached operation. So for us, you know, my background, I've got a long Oracle background, and there's one study that was done that talked about what is that difference, and they kind of average across 70 customers of theirs. This is a company called Hot Sauce. It's based out of Dallas. But it was about 28x slower from disk versus cache. For us, the number varies depending on the query, but it could be just 2x difference. So you might have an 8-second query versus a 4-second query. So I didn't answer your question, but
I think it should be, sorry, I think it should be in terms of clusters IOPS instead of just one single node IOPS.
Well, so we actually, so it's bandwidth is probably the better measurement for us than IOPS.
That's
because
the whole point of our cluster.
The point of clustering is to deliver more CPU and more bandwidth. But for us, it's not IOPS bandwidth. It's the bandwidth off the disk. So we do. I didn't jump into all the detail here possible. But in terms of when we do reads, we typically do range reads. Right. That's in sort of support of the idea we're doing big queries instead of small queries. And so we're typically limited by the bandwidth and not the IOPS, if that makes sense. But yeah, you're right. So, and we do have a data buffer cache in place. So you know that works like a traditional data buffer cache. So you can offset reads from disk with a caching memory.
Yeah, because right now we are in cloud computing. It's not like 20 years ago.
Yeah. No, I know.
Right?
Yeah. Yes.
Yeah, I have a question. What was the impact of going from closed source to open source? How does that affect your sales?
So as with many startups, the path is not always smooth. We went through some kind of changes last year, in the middle of last year, in terms of change in leadership. And that led us to the October open source announcement. Since then, we've been actually very, very pleased with the adoption. So, you know, what are the metrics you care about? So downloads, those are going up. Adoption, new customers, those are all going up. So we're very, very happy with the move in the direction.
And how's, so, okay, great. So your sales have gone up, your downloads and so forth. And then, how did it affect the P&L? Maybe it sounds like you didn't have a lot of sales.
Well, so we were always cost effective, and we're still, you know, so we do have an enterprise support license as a part of our business is how we sell those. So we were cost effective before, and we continue to be cost effective now. Our number did, you know, our average deal size changed by less than 30%.
By less than 3%.
Yeah. So for us, it wasn't. We suddenly were doing something completely different. It's suddenly we're doing something slightly different.
I think you can afford open source because you got funded again. That's
Yeah.
part of the reason.
Well, so the funding came after our decision process. So we actually went through the decision process and we got some additional metrics and then we made some decisions about funding.
Increase the VC community.
Actually, no, we have an individual contributor.
Okay.
So with MySQL, when we went open source, we lost money for 2 months, then we were back. But basically 2 months we didn't get almost nothing. But then we got more than before. Wow, good choice.
Good questions.
Question I got, so you guys open source, is there any difference now between the enterprise support that I get or just an open source or just the support that I get with it?
Well, so the open source supports through the community and the forums. You know, we do patch those in the same frequencies we patch everything else. With the enterprise, you get there's an enterprise management console. It's an external utility that lets you, you know, manage the cluster from a central point. It lets you do things like it reports on real-time and historical system utilization metrics, real-time and historical query utilization. So you can kind of say, well, hey, what happened, you know, a week ago Wednesday that made the server slow at 2 o'clock?
So you get basically with enterprise, you have the same database functionality, but you get additional tools and utilities.
Yeah, that's the idea, yes. Cool.
Thank you.
Thanks, everyone.